Good morning, ladies and gentlemen. So we are here today in the course of quantum transport, and I still have to finish lecture number 3. There's no problem because the topic which I outlined in the end of lecture 3 is essentially the same as in the lecture number 4. So we just go a little bit past this now. Right. There's an example of matrix current made from magic mirrors. I believe you don't remember already what is this, do you? What is a magic mirror?
The current gets reflected in the same direction that it came from.
Precisely, and also it keeps the same phase, which is impossible if it is the same wave. That's why in magic mirrors we intrinsically have two components of light. So there's two components, red and blue, so to say, and you can have a wave function which is two components. And from this wave function, you can make 4 by 4 current. And one can again put it into the Schrödinger equation and prove that at least in the absence of any agents which break time reversibility, the current is conserved. Very well. So what we have at this moment, we have found the quantum mechanics of any system, of any quantum system, eventually provides the opportunity for very many conservation laws. And in distinction from classical physics, where conservation laws are few, very fundamental, you know, energy, charge, name a few, money mostly conserves, but yeah, it's a rather complex question, so it's an approximate conservation of money. Money, yet more conservation laws we have in quantum mechanics, and most of them from this variety kind of, they don't have obvious physical no obvious physical quantity, useful quantity is associated with them. Right? But that we can neglect, we can use conservation of these currents to learn more about quantum electrons which are scattered in nanostructures. What I will outline now, it is a template of such theory. See. We have introduced matrix currents, and the counterpart of these master currents are going to be matrix voltages. I will call them using the letter G, because kind of historically and mathematically, these voltages originate from electronic Green's function. Some complex information about electronic Green's function, in principle at certain energy. Right, so we have matrix currents, and they obey a little bit funny property it is a matrix with a trace 0. It's okay, but the square of this matrix is 1. If square of the matrix is 1, you can say something about eigenvalues. Square of each eigenvalue is 1, so eigenvalues are plus minus 1. Right. And different choices of these matrix voltages allow to describe distinct physical situations. That's why it's not a theory about some physical phenomenon. It is a template. For instance, if we talk about classical conservation laws, you could use simple template, kind of sum of all flows gives you time derivative of a certain quantity. This certain quantity can be heat, can be charge, can be number of molecules in water, different physical situations, same template. So such template is presented here. I sketch some examples. I don't want to go into detail, just let me mention. Landauer formula can be derived from this approach if one uses such a matrix where F are energy dependent filling factors. If we talk about statistics of electron transfer in quantum circuits, minor modification of this matrix will allow us to describe also this. Suppose we don't care much about statistics, but we care about spin. Then this matrix will be divided by blocks, and each block is a matrix in spin space. It's just density matrix in spin space, which comes about. One could think of superconductivity, and much applications of this quantum circuit theory go to superconductivity, very compact description. Well, it's also a choice of this matrices. There's a number of structures associated with superconductivity, which is incorporated into this matrix. Good. That's a template which is up to us to make physical by making certain choice of these matrices. Right. That's one element of the template. Another element is the following. We are treating nanostructures as we have learned that everything what quantum transport knows about nanostructure is a set of transmission coefficients, right? So we can treat any nanostructure, the element of this nanostructure, as a black box characterized by set of transmission coefficients. Fortunately, the matrix current through such a connector is universal. It does not depend on a concrete choice of matrix voltages. That's we can substitute any matrix and get corresponding matrix current. We can describe many physical situations just with a single formula. Right. We could not say much at the moment about these T's, about distribution of these transmission coefficients, but we will apply circuit theory and we will get this distribution very simple very soon. in this lecture. Fine. That's yet another element of the template. And now the theory, which is kind of more or less taken from Gustav Kirchhoff. So how does it work in practice? Suppose you've got nanostructure to describe. You look at it, you recall the design, you think of a simple few element representation of the structure. Well, for instance, if I look at this one, I could think that these places work like nodes where electrons can be stored, can persist, while these junctions are perhaps better described as connectors. And those are leads. All right. So now I can draw a scheme. There are leads, receivers. There are two nodes and connectors, which are characterized by sets of transmission coefficients. Then there is a crucial assumption to make it practical. We say that each node is treated as a receiver and can be characterized by matrix voltage. Right? When does it work? There are requirements. It works in the situation where we are on the beginning of this lecture. In the situation when there are many channels and the self-averaging of phase vectors. These vectors are self-averaged, but they still have quantum waves. They have very complex spectrum of quantum waves. And the quantum circuit theory is to deal with this complex spectrum using conservation laws. All right? So we can go very practically. So for each connector, we have current, which is expressed through matrix voltages at its ends. For each node, we can sum up these currents, and owing to conservation, the sum of all these currents is zero. And that gives us a set of equations for unknown J's, for unknown matrix voltages. All right, so this is a lecture. I could perhaps immediately switch to lecture number 4. Again, these things are repeating. So with this template, oh, sorry, I didn't give you opportunity to ask questions. Or you're not questioning me?
I would like to ask you what you can use as a quantum circuit theory.
There are many uses. That's what you have presented today. Are two simple examples, rather physical, and there's some context to figure out some fun things to be assessed by quantum circuit theory. Two examples. First example is circuit theory of transmission distribution. It's kind of a little within quantum transfer. Because I have told many terms that individual conductor is presented by realization of transmission coefficient, while type of conductor is presented by distribution of this transmission coefficient. But it would make no sense unless we can characterize the distribution of this transmission coefficient. And circuit theory does this for any type of nanostructure for any design. That's one. Another example, which involves lots of applications in last decades, is a quantum theory of spin transfer. Conservation of spin currents. What you can do with conservation of spin currents, how you can treat elements which contain ferromagnets and normal metals. All right, that would be a little bit physical example. To some extent, it is too simple because quantum theory of spin transport is linear, which is not common case. If you remember this expression for matrix current, it was non-linear in terms of matrices. Right, so I will outline these two examples today. Fine, so let us go into this direction. And let me just, I think I have it here. Let me present just a kind of comparative table of the usual circuit theory based on Kirchhoff law and quantum circuit theory. Okay, what is common, what is different? Common thing that both theories have the same types of elements. Those are three. There are terminals, reservoirs, leads, whatever you call it. In the usual quantum circuit theory, there usually some leads, some contacts, terminals, which are biased at certain voltage. In quantum circuit theory, this voltage can also incorporate, say, information about fill-in factors, can depend on energy, can be more complex, but anyway, it is fixed in the reservoir, in the lead. Second element is a connector. In common circuit theory, it's a resistor. If you go to frequency domain, it could be also capacitor or inductor, an element. And there's a current associated with this connector, which is a function of voltages, usually a linear function, of voltages at both ends of this connector. Same is in quantum theory, but the variable here is a matrix. It's a matrix current, and it's a function of two matrix voltages at the ends of this connector. And there's also an element which is a node, right, if you think of a node in usual circuit theory, it's just not. It's just a point where things are connected, and it just characterized by voltage. Formally, the same is here. It is a part of nanostructure which can be characterized by a matrix voltage. But if you try to relate it to what we know about nanostructures, we understand that the node should have some space, right? Some space between connectors, right? When we discuss two connectors in series, we have to think about the space between, which can be characterized by one base vector, or if you have many channels, by the whole matrix unitary mixer, right? So this is the node in with physical reasoning. Good. What I have here is a condition of applicability. All conductances must be larger than GQ, which means that there are many channels, complex pattern, many phase factors involved. Nevertheless, we can study it, we can make conclusions about these properties of these wave patterns using using conservation of matrix counts. That was a template, so let us make it concrete. I told that specifying the template means choosing the matrix voltage, and I choose it now just purely from mathematical opinions. I swear that I can have any physical meaning for this quantity, but it's fine. So some things in physics which don't have physical meaning, but help us to understand this physics. So what do? I would write a matrix, simplest matrix. What's simplest matrix? Matrix of dimension 1 would not fit here because the trace has to be 0. The whole matrix must be 0. So I take a 2 by 2 matrix. And this family of matrices satisfies the properties. Trace is 0 because diagonal elements are all 0. And if you make a little piece of algebra, if you compute the square of this matrix, it's gonna be 1. At any letter phi, which I will call phase, again, it's not some physical phase, it's just a letter which I introduce. Right. Then what I do now, I take a vector characterized by a set of transmission and I take these two Green functions and given the formula, Landauer formula, I compute the current for this. It will depend on difference of two phases, phi 1. Very much like linear current depends on the difference of voltages. It will be a matrix of very simple structure. If you look here, you recognize that this is just proportional to what people call sigma z. All this. Right. As such, it can be treated as a scalar. It's always scalar times sigma z. And what kind of scalar is it? It is a function where you can find phi, and transmission coefficients. Good. What does it mean? It means that if you know transmission coefficients, we can sum up or integrate if it is a distribution and get a current as a function of phi. All right, that we can do, that's perhaps not very interesting. What is interesting is that we can do reverse procedure. If we know I of phi, the whole function, we can figure out transmissions, the whole transmission distribution. Here it is, it's a plug playback formula, which looks pretty complex, and it involves complex numbers, complex values of phi, but it is not something magical. In fact, I don't want to write this formula, but just give you its origin. You know, theory of complex functions, right? And it's important in theory of complex functions, the existence of poles, which are zeros of the denominators. Here, it is a denominator we need, and as a function of complex phi, it will have a pole, and the position of this pole will be given by transmission coefficients. So if we can find the distribution of poles of this function, we will find the distribution of these transmission coefficients. And this is the formula for that. Here, there is some common function, common factor, which does not depend on peculiarities. At the moment, we just take it like this, but we will show very soon with our own hands that this is distribution function of a diffusive electron. Right. Okay, so how to use it to compute transmission distributions? We can start with some basic types of connectors which we know. Simple things which we can estimate right away are tunnel junction and quantum point contact. And in several steps you also reach another basic element, diffusive conductor. All right, so it is something strange. You didn't expect this transparency. All right, write this here. Actually, I don't remember why it has to be here, but anyway, let us mention this property. It all works in the limit of big number of channels, in the limit when Ohm's law is valid. And the simplest exercise about this theory is to derive Ohm's law. how one can do this? I guess it is it's better to start with this formula. In this formula, I will go to the limit of small phi. Let us see. Is accuracy up to terms phi to the second power? The denominator just becomes we look at the denominator, we take the limit of small phi. How much is this?
1.
Yes. Here we have the n, and instead of sine, I could just write phi. Conductance quantum. So the coefficient just becomes the conductance of corresponding connector. So that's why if you just take the limit of small phi's, it will correspond to usual circuit theory to Ohm's law. Yeah.
But we were talking about German structures having a large channel.
Yep.
Does it hold for quantum contact as well?
Yes, it has to be done. Sure, it's a quantum point contact, which is a constriction, but the constriction is pretty large.
Can you quantum
Yes, why not? As far as electrons which traverse this contact are quantum waves, I can call it quantum. Also, one can see quantizations. That will be quantization by small steps at the background of large conductance, but still there will be some quantization. Good, so that was correspondence with Ohm's law. Now we can just compute the dependence of I on phi for a couple of examples. Let us take quantum point contact. We can write the distribution. Some channels are open, some channels are closed. They correspond to zero transmission. They don't contribute to quantum transport. We care about open channels, which give the conductance of quantum point contact. All right, so we take this formula, we substitute one here and here. Good, just some function. This is non-linear function. Pay attention to this. Tunnel junctions. It's even simpler. In this case, all transmission coefficients are small. To that end, we can neglect this term in the denominator. Then let's can sum up all transmission coefficients to conductance. Here we are. Why do I call it theta here? It has to be phi. Oops. Right. Now important point, which kind of enables the use of quantum circuits of this transmission distribution theory. It's about combining two conductors or several conductors. What is the trick? We know transmission distributions in both connectors. Now we can combine it, and we compute the current as a function of phi for the compound system. Then we can use playback formula to get transmission distribution of these two combined connectors. So, using quantum circuit theory, we can compute this distribution for any possible design. Let me explain how to do it for two connectors. Good. So we have bias. We have we fix these parameters, phases in both leads. There are two connectors, and there is a node between these two connectors. It is at some phase which is not known yet. We don't know voltage in Kirchhoffsky. All right, well, how we can figure that out? We write the current in one connector as a function of phase, write another current, and by virtue of conservation, these currents have to be the same. And this is an equation for theta. This is an equation for theta. We can find the total current as a function of phi, and finally get to distribution. All right. So, till the end of this part of the lecture, I will just do it for simple pairs of actually not pairs, also for many connectors, and we got some physically significant things to learn. Right. I could do it for many connectors in series, right? So then I would just have more variables, more currents to equalize, and I can solve for all these phis. Yeah, in general, it's plenty of equations. There's a simple way to make it solvable for us. What is the way? Just to simplify it a bit and assume that all connectors are identical. Fine. If all connectors are identical, they kind of equal. They're equal, and the drop of voltage of phase across each connector is the same. It is the same, we can express it. This drop is the full phase divided by a number of connectors. So what is the current? The current is common for all connectors. It just goes through. It is the same. And it can be written like this. What does it mean? It means that for many connectors, for many equal connectors, but I will argue that it will be the same. The resulting circuit is linear in phi. And one can regard it as a definition of diffusive. Look, I didn't talk much about diffusion, about an electron which scatters on impurities many times and finally diffuses at sufficiently large time. That is described by diffusion equation. We will mention several times, but not in this context. So how to make it a little bit intuitive? Well, in this case, in order to traverse the whole chain of connectors, electron will have to bounce many times in these nodes. So its motion through the whole circuit will be necessary diffusive. It's like qualitative argument. Good, so it's linear, and if you use Landauer formula, we got this distribution of this time, which I believe I plotted at some stage. Right. So this is this ends the set of elements. So the basic elements are tunnel junction, diffusive connector, and ballistic connectors. Let's combine them. All right, this is the formula which I was trying to reproduce. So this function, if you look at it, it has two divergences at small t and at t equals 1. Good. Counter question, which you can perhaps figure out by yourself, but let us talk a little bit. What will happen if we will combine two diffusive connectors? I can argue it in very simple terms. The resultant circuit, since we combine two linear elements, will be linear. And we know that linearity with respect to phi is a signature of diffusive connector. So if we combine diffusive connectors, we always end up with diffusive connector. What is the connectance of this connector? Oh, don't vary. It just satisfies Ohm's law. Fine. A little bit more interesting example. Two tunnel junctions. Good, so we know the currents in each tunnel junction. We can use it to determine unknown. Unknown is phi for a change in terms of external parameters, in terms of theta. Right. We can use playback formula to arrive at the following distribution. It looks a bit like diffusive if you just look at it and try to analyze it. I see there is divergence at in the limit of small transparency, and also similar square root. It's only important that this square root doesn't end at 1, but at some critical transmission coefficient, which depends on asymmetry of two junctions. Look, I better plot it. Here, there are several plots. For symmetric situation, we have transmission distribution which diverges at 0 at 1, similar but distinct from diffusive distribution. Further things happen if we have different junctions. Then the distribution, let me take 0.1 of a symmetry. The distribution just ends at some critical value of transmission coefficient. There are no channels with high transmission coefficients. Good. It looks a little, perhaps as a new result for us, but there is rather straightforward link with something which we know. Who remembers this formula? Quite. Ages ago, we've been looking at, that was in the beginning of lecture 3 and then at the end of lecture 2. We've been looking at transmission coefficient of two conductances in series. There was a story I told you about A, B, and end. So this end is a phase factor here. You remember the story? Fine. So in fact, what we have figured out then, that as a function of this phase factor, there were peaks and dips. The peaks hit one only if the junctions were symmetric. If they were not symmetric, they were restricted. And in fact, in this distribution, we just see the peaks. The only thing, there's plenty of these peaks, series of these peaks, corresponding to different transmission channels, so they all mess up. But yeah, it's the same distribution which we know. Just average over all passive localizations of phase vectors. Good. Let's have a break at this point. 7 minutes break. What it is. Very good. Get our junctions. We use this quantum theory. We have figured out what is the transmission. What is the most surprising thing, perhaps? It's a surprise which we have learned about already several times. We have two connectors with very small transmission.